We won't go into the details of modes of natural variability, but we will quickly see them just so that we are aware of global warming happening on top of these. And as I mentioned before, it's always tricky to understand how global warming is actually modifying the natural variability patterns. That's not easy to do. We will see a little bit more about that later. So I took the figures from elsewhere and not from the book chapter, but the message is the same. What you do is use things like statistical tools of spectral analysis, empirical orthogonal functions, multi-channel singular spectrum analysis, and so on, to extract the various patterns. So if you have a time series of sea surface temperatures or surface temperatures going from, let's say, 1850 to here 2014, it has grid distribution, spatial distribution, latitude, longitude, latitude, and time distribution. These statistical tools will let you extract the low frequency variability here. So that shows you the trend or the decade to decade variability. But again, the question is how the decade to decade variability is being modified by greenhouse gases and global warming. And it extracts this low frequency variability which has no trend in it. So in terms of temperature anomaly, you can see that this pattern is corresponding to this particular time series. So if you multiply this time series to this, you will get the value for that particular year, for example. And this is the low frequency variability, which is a time scale of decade or two, depends. So from the data you can extract these time scales, and then you want to look for processes or modes of variability or mechanisms which generate these low frequencies. Always keeping in mind that atmosphere has no memory, so it cannot produce low frequencies. So it has to come from glacier melt, vegetation changes, or ocean changes. So ocean can control coupled variabilities at low frequencies. And then this pattern here is showing this high year-to-year variability, the high frequency. And for those who know what this is, this kind of warming or cooling. So remember that this time series is positive or negative. So when you multiply, you will get either positive anomaly or negative anomaly. It's the same for all of them. Okay, so and there is statistical significance issues in the regions where there is no color. Okay, you have to be careful that there is often not enough data to say confidently that there is a change there. Okay, so this pattern here corresponds to what we call the El Nino or La Nina or El Nino Southern Oscillation. I have detailed podcasts on El Nino and La Nina and so on that you can look up, but this is the year-to-year variability. So El Nino happens here in the Pacific, sometimes warming or cooling around, warming around the dateline, sometimes warming extending all the way to the coast of North and South America. Climatologically, if you remember, the temperatures are cold here. Galapagos is cold, upwelling, primary production or photosynthesis, rich biodiversity, whereas here you have warm waters, warm pool, moving with the sun, coral reefs, Great Barrier Reef, and so on and so forth. A lot of rain. There's no rain here, and so on, right? So these are the predominant modes or patterns of variability. There are other variabilities, obviously, in the Atlantic, at the high latitudes, in the Indian Ocean, and so on. And you also see that the so-called secular trend, which means it's over a certain period, is higher at high latitudes here in the Arctic than in the tropics for multiple reasons, because there is ice albedo feedback happening here, right? If you warm a little, you melt ice and snow and you reduce the albedo, absorb more energy, so you get more warming. In the tropics, temperatures are warmer, So warming, little warming can produce atmospheric convection, which tends to take away the energy, and so on and so forth. So the consequences of warming will also be different. So when we talk about global warming, we should always remember that we are averaging over these cooling here, cooling or no warming here, more warming here, less warming here, and so on. So the question is, how are these natural modes being modified by these additional warmings happening because of human activities? So this is another way to look at it. This is looking at sea surface temperatures now, no land temperatures. Global mean sea surface temperature shows a warming trend, so it's showing the data itself and the time series, or the principal component of the empirical orthogonal function used to extract the dominant pattern. Okay, the same thing here. These are the time series, or the principal components, or the canonical modes, or canonical correlation CCAs, and these are the spatial loading, or the spatial pattern. So you have to multiply this to get the answer. So there is a whole debate about whether global warming pattern should look like El Nino or not, and so on, which we won't get into. But the second EOF captures the interannual variability, or the El Ninos and the La Niñas. So El Nino is when it's warm here, and La Niña is when it's cold here. And you can see that there are apparent changes in the frequency, duration, amplitude, and so on, but it's not clearly known whether that's natural variability or modulation by the global warming. Complicated things. Okay, so this shows another pattern called the Pacific Decadal Oscillation, which you can see has some similarity to the El Nino pattern. So there is this AMO pattern, Atlantic multi-decadal variability, which has a huge spatial loading here with a different time scale than the Pacific Decadal Oscillation. So unless we know the processes that select these time scales, it is hard to know if they are oscillations or they are episodic events, because the data is not long enough. If you want to call this an oscillation, then you need at least 2 cycles to be extracted from the data, and you can see that we barely have 1 cycle here. PDO offers multiple cycles, but we still don't know what the mechanism is which would produce this time scale and this pattern. Okay, some people argue that it is related to the El Nino and La Nina itself. Okay, so complications, but we know a lot, and this shows a good way to look at polar amplification. So it starts in the 1880s, I think, and you can see that lots of negative blue colors in the beginning end up becoming almost all red, with some exception here, and the polar amplification is very clearly seen. So natural variability is now happening in a warmer and warmer climate. So the question again, to repeat myself, is how is global warming affecting natural modes of variability? How can we say for sure that global warming is happening? That's what gets us into detection and attribution, which I will do in the next podcast. Okay, so we have very good theories for things like El Nino and monsoon, even though they are not complete. We can explain a lot of things about them, but lower frequencies like PDOs, AMOs have some work left to do. And then the question is, if there is a warming on top, how can we be sure that it is in fact related to human activities, human emission of greenhouse gases, and so on? So that's the idea of detection and attribution that I will show in the next podcast.